So how can you get energy out of gravity? It seems ridiculous. Well, the basic idea is you drop something. If I take a rock and drop it on my foot, you heard the bang. That energy that made that bang and the dent in my foot came from somewhere. In this case, it came from gravitational potential energy. So when this is up high, it has gravitational potential energy. As it falls, that is converted into kinetic energy, speed, and then when it hits my foot, ow! It's converted into breaking chemical bonds in my foot, sound waves, heat, and so on. So if you do have a lot of gravity, and you drop things down the gravitational potential well, it can produce power. On Earth, this is how hydroelectric power works. We let water fall down, that makes power. If you have a really heavy mass like a black hole, you get a lot more power. So say, for example, there was a black hole up at that dome over there, and I had a peanut in my pocket. What would happen if I let go of the peanut? Well, the gravity of that black hole would suck the peanut towards it, and if someone was standing up there in front of the dome, put their hand in front, what would happen as the peanut went through their hand? Well, you get a peanut-shaped hole, but also you get an explosion equivalent to about a 10 kiloton atom bomb. Because by the time the peanut came close to the dome, it would be travelling nearly at the speed of light, and the kinetic energy of a peanut at that speed is so big that it would have an explosion that would devastate a large city. So the motto is, if you're near a black hole, keep your peanuts in your pocket. So how much energy can you get out of dropping things into a black hole? So let's imagine we've got a black hole here. We can't see it, of course, it's black. This radius is the Schwarzschild radius, the radius of the event horizon, the line of no return. Once you're inside that, you can't get out even unless you go faster than light. And Einstein's equations tell us that radius is 2g, the mass of the black hole, over speed of light squared. So once something's in there, we can't get energy out. But let's say we had an object sitting at rest out here at infinity. The gravity will start pulling it in. It'll get faster and faster and faster. And so by the time it's just above the event horizon, it has a lot of kinetic energy. It's moving really fast. And if at that point it should bang into something else, say another object coming in, or rub against something else coming in from here, in principle that energy could be released. So how much energy does something have if it falls from infinity to just above the event horizon? Well, the easiest way to calculate this is using potential energy. Gravitational potential energy, you're usually used to it as potential energy equals mgh. That's the form normally used for equations on Earth. This, however, is just an approximation. It's valid for when things are near the surface of the Earth, but when you're moving around in space, you need to use the full form of the equation, which is the potential energy equals minus g, m of the black hole in this case, m of whatever it is that's moving around, over the distance. And this, it turns out, acts like that when things are moving around a very small fraction of the radius, like within a room on Earth. But this is the form we'll need to use. So at infinity, potential energy at infinity, r is infinity, so that equals 0. Potential energy at the Schwarzschild radius, the event horizon, equals minus g m black hole, m of whatever you're dropping in, over the Schwarzschild radius, rs, which is 2g m of the black hole over c squared. So that is equal to, g's cancel, the mass of the black hole cancels, it's just mc squared over 2. So if, with the minus sign there, so the difference will be this minus that, so change in energy, that's the amount of energy that's released, is just equal to half mc squared. So what that means is you're releasing 50% of the rest mass energy. Mc squared is the total energy, and 50% of that has been converted into potential energy by the time something hits the event horizon. So that in principle is how much you could release. Remember that nuclear fusion, it was only 1%. So in principle, gravity is great. It can get 50 times more energy per unit mass out of dropping things into black holes. But that's only if all the energy as it falls in can be released somehow when it gets to the event horizon, and that's a big ask.